Sven will tell us what machine learning identifies symmetries, integrability of physical systems.
Yeah, right. Make sure my screen is going. And so, okay, yeah. Okay, good. Yeah, thanks, Vishnu, and thanks everybody else for setting up string data this year. I think it's a, always a wonderful conference, and it's already the 4th year that this has been going. To set the scene a little bit, I like to, put this a little bit into perspective, and the perspective I want to share here is that of, what kind of things we are aiming at in theoretical physics. And so I like to start with this job description by Steve Weinberg on our purpose in theoretical physics is not to describe the world as we find it, but to explain in terms of a few fundamental principles why the world is the way it is. And these are often things, we're trying to do in one way or the other. And I think one of the questions we are asking is whether machine learning can achieve this. And if we can really achieve this, I think it would be truly remarkable, because we really, would have set up something which is explainable AI, where we can identify these principles and where we can see, what is which principles are at the heart of, understanding these systems. And obviously, it's a really tremendous journey if we, use ML to do this, because we can look for really new physics, and it will be tremendous to see new discoveries made by AI in terms of physics. So the question I want to talk about is today the following. I mean, first of all, we want to look at problems which are made for ML. And for me, this is always like looking at high-dimensional data sets in one way or the other. And the string theory is no exception to high-dimensional data. We know a lot of examples of this. There's a lot of work going on, which also already has been mentioned in terms of, sampling string vector. And I just highlight the talk. Would like to stress, please come to Gary's talk on Thursday. We'll talk a little bit about our work on sampling string vector with RL and genetic algorithms. And then there are lots of talks on getting numerical Calabi-Yau metrics and so on. These are all really great examples. This talk is going in a slightly different direction, in the sense that I would like to focus on how do we extract domain knowledge and biases with machine learning. If you want to ask this in a very simple, what does this mean? What am I doing? Is, for instance, I'm asking the questions, can I identify the symmetries of a system that are underlying it? Why am I bothered about this? Is because such functional biases on particular symmetries are really the reason why a lot of deep learning architectures do work tremendously well. And there's a really deep connection with symmetries going on. This is the translation invariance in CNNs. But this is going much further if we're talking about the field of geometric deep learning, where in various areas, different settings, different sets of symmetries play the crucial role. And this is naturally connected, if we're talking about symmetry biases, with what we are doing in physics all the time. Namely, we're talking about symmetries being organizing principles of our dynamics. So identifying those symmetries is twofold interesting, one in learning physics, but also in building machine learning architectures that are very efficient. So today I'll be talking about work done in collaboration with Max Sivery, who is recently graduated, and Dieter Lüst. So this is basically the question, like, what do we do when we do not have domain knowledge? And how can we use AI to identify such correct domain knowledge? And I think this is, a very interesting question, which we can ask in the context of physics. Basically, do we see some symmetry structures or other structures that, can we discover those? And now, if we want to set the scene a little bit, this is basically, you can ask this question across different areas of science. If you would have asked something similar in chemistry, you would have asked pre-1869 of discovering, say, a periodic table. If you would have gone particle physics way back, you would have asked about discovering standard model dynamics and the Lagrange, the underlying symmetries organizing the physics there. So the question is, okay, which tools do we need to make such discoveries in the 2020s? And for me, this is really finding mathematical structures to describe these systems more efficiently. And I can ask this in a very much variety of systems. And in the end, it's the same technique or same techniques that we can apply. So we can apply this in astrophysics. We can talk about the strongly coupled systems like QCD, but we can also ask about this in our favorite Calabi-Yau manifolds. And so our approach is really to look for symmetries, look for dualities, and particularly today I'll talk about searching for integrable structures. And this is basically, you know, identifying such good functional biases that you can build into your architectures. So let's get started. So this is the first work that we did on this. This is about identifying symmetries from looking at the embedding neural networks fine. So this is, I'm not talking about the SISI example, but we did some examples in this paper about SISIs as well, that Yang mentioned in his just a talk beforehand. So the question is, you know, how do we search for symmetries if we don't know about them? So here in this simple toy example of standard Higgs potential, the situation boils down to obviously identifying such orbits. And that's here what we can do by eye very simply, but we want to do this with a machine, and we want to obviously do this on other data sets where these symmetries are no longer as transparent. So what are the crucial steps that we need to do is, first of all, we need to identify what the invariances are. So we need to identify points where properties are being shared. And then we need to understand which structure is behind such an invariance. So what we need to do this and is to group things together that have the same meaning. And this is rather similar to the Siamese network as well, in the sense that what we are doing is we're looking at the embedding layer and the structure that the neural network adapts there in order how it's clustering things with the same meaning together. So this is obviously something which goes back in the machine learning literature, namely to things where which you can look in language processing, where you have meaningful embeddings very deep in the neural network. So for instance, you can look at where words like London and Paris are embedded and where England and France are embedded, and such equations then start to make sense. Similarly, you can apply this to other data sets in science. In particular, this has been used in re-identifying the periodic table. Now, what we wanted to ask in that paper is, can we search for symmetries in this way? And the answer to this question is yes. We can do this. And so what I'm showing you here is, for instance, in this Higgs potential example, where we're doing a simple classification task. So we're classifying for the value of the potential, and then ask what the embedding is finding. And what you can see is, if you dimensionally reduce this space, is that it's clustering these symmetry orbits together. So that's kind of the first step. And you can also do other techniques in the sense of like looking at what is quantifying these clusters better, which we also did. But let's look at the second part of this thing, is basically how from such a cluster, how do you identify the symmetry? So you are in the input space and you have some point cloud like this, and you want to know what symmetry is underlying this story. So what we're doing is determining essentially the generators that connect these various points with each other. And you can do this procedure. We give some iterative algorithm to basically do this. And by doing appropriate dimensional reduction, we identify the dominant generators of this whole problem. So an SO2 example is kind of trivial, but you can do this for other examples like SO4 or SU2 or SO3 that are underlying ancestor setup. And you can identify this, even with relatively a lot of noise, relatively few points, you can still characterize the generators very accurately. Now, this is one set of the story. Another set of the story is to look at different types of data input. And that is just basically identifying symmetries just simply from looking at samples of phase space. So this is a story which goes back to Battaglia et al. In 2016, where the question is asked of whether, by looking at some snapshots of a dynamical model, is whether you can identify the underlying dynamics and predict, obviously, the next time steps. So what we'll focus on here is a subset. So we're looking at already a dimensionally reduced input space, namely already in nice phase space coordinates. And then the target is to predict the next time steps of this system. So why am I talking about this? Is basically because this is a perfect example where our physics bias helps us for making such prediction. And this is the story of Greidanos et al. In 2019, where basically putting into these systems additional bias, namely energy conservation, that this already helps in predicting the dynamics. So instead of using a network which predicts P dot and Q dot directly, what they instead do is predicting the Hamiltonian in the first step, and then use auto differentiation to predict P dot and Q dot. So if you put this into, just put this on a gravitational two-body system, you can see that you are gaining significant improvement with using this physics bias in the system. Now, what I wanted to ask is whether we can learn actually more structures from samples of phase space and utilize those. So what they were able to do is to train a neural network to find the Hamiltonian of a system just with these phase space points. And what we asked is whether we can use other interesting structures. In particular, can we learn the symmetries of the system? And so what, we're going back to classical mechanics then effectively is basically that we have to, we know that conserved quantities have a particular structure, namely that the Poisson bracket of such quantities with the Hamiltonian vanishes. So by learning appropriate coordinates, we can basically reveal such symmetries. And for these, we have to do the appropriate learn the appropriate canonical transformations to do this. So what are the key steps here to actually get this to work is basically, to formulate it as an optimization problem. And then in the second step, once you have this, to ensure that your architecture can actually learn this. Then once you have it, you can go about and analyze it, and you can actually also look how much benefit you gain from in predicting the dynamics by utilizing such symmetry structures that we all love. So here's an overview of what we did. So basically what we did is we replaced this Hamiltonian neural network architecture with an architecture which learns in a first step appropriate coordinates, and then in the second step learns the Hamiltonian of that with those coordinates. And what we need to do is really use this additional property on these coordinates, namely that the Poisson bracket has to vanish. And we have to go through a little bit more architecture. Basically, you have to look at, what are the conditions on these coordinates that have to be satisfied. And there are a few more that you then have to code up and make sure that they're satisfied. Effectively, why this is working, as you can see here on this, as this illustration on the two-body system, is the bottom one here is our architecture in comparison to the Hamiltonian neural network. This is giving better predictions. I'll come back to that as well. But basically, the idea why this is working is that you're constraining your motion on again, a subspace in phase space. And this additional structure that is taking place due to these symmetries is that's what you're utilizing. So there are two kind of benefits that you can have. One is really that you can reveal by using very simple formula fitting what are the conserved quantities that you learn from the system. So as no surprise, what you see is that you see total momentum being conserved in various directions, and that you see angular momentum being conserved. I like to put these numbers here because this is really what's coming out of these networks. And you see that you have to think a little bit on that there are some linear combinations and so on, but you also see a little bit on the accuracy of the predictions that you're getting. And then finally, the second benefit from this is really that you can quantify how much better these the predicted trajectories are when you use these conserved quantities in comparison to these Hamiltonian neural networks. And here are the mean squared errors, for instance, for this Hamiltonian neural network, and then for symmetry conserved neural networks. Now, this is very interesting, but it's at a very classical mechanics level. So the question then, what we're asking is, okay, how can we push this forward to actually get new insight into systems that we haven't known before? And that brings us to earlier this year, where we asked the question, okay, if we can learn symmetries, then there's a natural consequence of continuing this question is to search for integrability of a system. So basically, in a nutshell, what we have to look for is that the system is integrable, so we need as many degrees or as many conserved quantities as there are degrees of freedom. So effectively, what we need for the system that there are n independent, everywhere differentiable integrals of motion. Okay, but this is, especially if you're thinking about field theory, a little bit not necessarily the best language to talk about. There's an alternative way of talking about this is basically to search for what is called a Lux pair or Lux connection. So there's a matrix valued equation which has this structure, and then the conserved quantities can be revealed by taking the kth power of this Lux matrix and taking the trace of this. So to give you a simple example of how this works, it's just if you plug in the harmonic oscillator, this is a Lux pair that you can write down, and then you can see that the Hamiltonian arises nicely as a conserved quantity. Good. Why is this interesting? Is basically Lux pairs are or integrability in general is underlying a lot of very interesting systems. So knowing about the integrability would be very nice, but there's in general no algorithm to construct Lux pairs. So if we're looking then, for instance, at Beiser's lecture notes on integrability, he calls that the concept of Lux pair does not provide a means to decide whether any given system is integrable unless one is very lucky to find a sufficiently large Lux pair. So actually, if you need to be able to find them. And so this is a search problem effectively. And again, that's what we ask the machine to answer. So how do we do this? Well, we can formulate the search again as an optimization problem. So if we want to have Lux matrices, they should satisfy this equation. So this we can formulate as a loss as such, and not a large problem. But then there's a second condition, which is basically that this should be equivalent to the equations of motion. So this should not be just a trivial solution here, which obviously a neural network would easily pick out, but you rather should have a solution which gives you the equations of motion. So how did we deal with that? We dealt with that in the following sense, that we're looking for Lux pairs which have a particular structure, namely that include in L these variables xi somewhere. So this is essentially the left-hand side of the equations of motion that you get. And the right-hand side of the equations of motion is captured in this commutator of L and M. So with that at hand, we formulated appropriate loss functions that actually give us this problem that satisfy this. But this was not even enough to get this optimization problem to work for us. So we had to put a bit more crank on it. And what we did is we included and forced the network to avoid mode collapse. So in the sense that, we definitely forced it away from zero. So that was then our total, yeah, thanks. That was our total loss function then that we got. So here are some results. So if you look up, do this kind of scheme now for harmonic oscillator, you can learn L and M, and you can then obviously, do your appropriate consistency checks, and you can see that things are working, and that you get the Hamiltonian out, for instance, in this case, as the conserved quantities. And so that is nice. Now, obviously, we don't want to just do a harmonic oscillator. We want to look at various other examples. So we looked at KdV, which is in field theory. We looked at the Heisenberg magnet, and we looked at the nonlinear sigma models. In particular, we looked at the Sine-Gordon equation and the principal chiral model. And for all examples that we looked at, we got this to work. Effectively, what we're just using here as training data is just literally phase space examples, right? So there's no knowledge about Lux pair or about the solutions that is going in. The only availability what you need is you need phase space samples. For that, you don't even need to know the Hamiltonian, right? If you have some other way of just knowing phase space samples, that is sufficient. Now, here's an interesting story of this. It's not just you can learn the Lux pair of a system, but you also, I think one interesting aspect is that you can ask now whether given a certain perturbation of a system still keeps an integrable system integrable. So for instance, you can ask to a harmonic oscillator, a 2D harmonic oscillator, whether this perturbation, whether it remains integrable, or with this perturbation, whether it remains integrable. So what we do is we initialize our network at a known solution for an unperturbed system, and then see how it reacts to samples from a perturbed system. And here I'm showing you results on with varying values of this epsilon parameter, how the system reacts. And it definitely reacts differently to these two types of perturbation. And so, whereas the integrable one, it really goes down to something really reasonable. So this looks very much just as some numerical error that you can push down. And so this is something that looks very integrable, whereas the non-integrable one and really can't deal with that. Yeah. So what this tells you is that this is not necessarily conclusive that this is not that this perturbation could still be integrable. Your Lux pair could not be large enough, but it can be a positive, give you a positive answer. Good. So I think that's very interesting because it allows you to search through a list of perturbations, whether they're integrable or not. Now let me conclude and provide a little bit of outlook. So I hope we all agree that biasing our networks with physics knowledge is very good and very useful. We should all be doing this because this gives us very efficiently results. So this can be done on a simulation level. This can be done on a classification level. This is something we need to do. But what is also possible is that we can actually use machine learning to find these biases. So what we can do is we can learn the Hamiltonian, we can learn the symmetries of a system, and this is really possible in an unsupervised way. And I think that's very exciting because this really opens the door to searching for these structures. What we have done is obviously, on very simple examples where we know the structure to build up this technology. But I think that's, these are the first steps we have to do. So concretely, what we've done is we've looked at, symmetries from just looking at the embedding layer. and we've looked at symmetries, getting them from the phase space samples. And we've, in terms of integrability, what we've done, we've looked at, we've set up again the machinery to search for Lux pairs. And what we have done is we looked for perturbations, whether we have a machinery to look for integral perturbations with this framework. So with that, I would like to thank you. Here are the papers, and if you love these kind of talks, I would also like to, invite you to Physics Meets ML to tune in and, come to our online seminar series there. So yeah, thank you very much.
Thanks, Sven. Any questions? Eva?
That was very interesting. Thanks. I wonder if you could make progress on almost the complementary question here, which is chaotic behavior and mixing timescales and that sort of thing. Can you see correlations to K in the case where it isn't integrable?
Yeah, this is a very interesting question, right? So you can really look at, train with systems in principle, where it's really in an integrable regime, and then ask, okay, how does it behave, when you crank up the system in order to, go to chaotic behavior? Very interesting, question. We haven't looked at it yet carefully. I know that, Max Tegmark has been pushing a little bit in that direction, but I can't give you a concise summary of, all the things he has looked at. But this is definitely really, an avenue, especially like with this integrability stuff. Like one thing is, you have the handle in your hands about, for instance, searching for integrability in a subsector. Yeah. So imagine, you want to restrict yourself to a very symmetric subcase, where you have some integrable structure. That's something, you can train your setup, you can train your network on to find it. And then you perturb the system, right? And you can see how things react and how things are going. And yeah, that's definitely, a direction for the future.
Thanks.
Ning?
Hi, I had a question about how you foresee this extending past the classical regime, because I guess I can see how this would work pretty well for classical physics, but I guess I don't quite see how, if you had to incorporate quantum effects or quantum corrections, you would do the search. Do you have any comment on that?
Okay. Yeah. So, good. Yeah. Thanks for the question. I mean, in terms of, yeah. So I think this is a, it's a very, important question, right? How we can, say go from classical integrability to quantum integrability. But also, if you're asking before that about, looking from systems, say quantum mechanical systems, learning the Hamiltonian there and learning the symmetries underlying those. So I think I haven't got conclusive answers yet in the sense of what's going on. So my approach here is to go from a case to case and see how things behave. But so in general, when I say, I can't, like, again, I think the important bit is like also what I said is, one is to set up the optimization problem, and then second to solve it, to see that it actually works. But the point here is that you would so there is no, like, when we set up this optimization problem here for this kind of, for L dot being the commutator of L and M. Now, if you're going to the quantum version of it in integrability, there are different conditions that you have to satisfy. But in general, this framework of writing down the optimization condition, you can still do, and you can still, define your optimization problem. Whether you can solve it, that remains to be seen, and it has to be studied in examples. But a priori, I don't see an obstruction. That's how much I can comment on it right now.
Okay, other questions? Not, let's thanks Sven again, and we'll resume in 27 minutes.